My name is Austin Buckles. I'm the sales manager at DB Sales. I just wanted to do a little brief introduction. Today, we have Ken Eggleston from Mestek, who will be talking about commercial inverter heat pumps, their applications, how to use them in the industry, and maybe a little bit about how the growth of this product is we're seeing just tremendous growth in this product in California, at least the Southern California market, as we move into electrification in this area. Throughout the meeting, if you do have any questions, feel free to type them up in the Q&A box. You can send it to the chat. Either way, the panelists will be monitoring it, and we'll try and stop Ken at an appropriate time so he can answer that. If it's something that I can answer or one of the panelists can answer, I'll take care of it for you through the text. But with that, I will hand it over to Ken and we'll get rolling. Thank you very much.
All right, thanks, Austin. As Austin said, my name's Ken Eggleston, work at Mestek. So I'm gonna give you a good overview of our offering on the air-to-water heat pump, and just kind of start off with just a brief history of Mestek, which is our parent company to the RBI line, ATH line, and the Smith Boiler line. So Mestek was established in 1946 out of a rented garage, and at that time he was developing fin tube baseboard, which might not be a big thing for you guys out in California, but where I live here in Massachusetts, it was a thriving market back then and still is to this day. Mestek, as they grew, were composed of 40 plus different manufacturing companies, and it's kind of divided out into our HVAC division, which I'm part of. We have a machinery division, louvers and dampers, architectural, and then our control technology group. So on almost, I'd say like 95% of the products that Mestek offers out to the market, we're making our own master controls to that. We're still using the Honeywell stuff and things like that in particular situations, but mainly the brains to our product is all done in-house, which is nice because you can adapt different applications as they come up. So not to go too crazy, I just want to touch on the Mestek Boiler Group, which this air-to-water heat pump is part of that. So we have our Advanced Thermal Hydronics division, RBI boiler and water heaters, and then the Smith cast iron. So just again, a little touch on the ATH product, which is your condensing cast iron boiler. This was invented really in 2004. And we have, I don't even know, probably 30,000 of these boilers out in the market to this day. One of the cool things about it is it's always being updated throughout these years. So there's a lot of components that have changed to just update and to match what our competitors and other manufacturers are doing out there. So we offer two series, the 90% efficient thermal, which is your standard KN ranging from 200,000 up to 4 million BTUs. And then we have our KN series plus, and the plus just has a secondary stainless steel heat exchanger on the back, giving us efficiencies up to 96%. The size range on that is 600,000 up to 400,000 BTUs. And on this product, we just recently released our 10-to-1 turn down with O2 sensing. So just keep that in mind. On to the next would be our RBI boiler, which is what the heat pump is listed under. This manufacturing plant really started as a copper fin product in the water heating sector. But again, as things progress, we are now into the stainless steel fire tube, water tubes. On the water tube side, we can offer boilers or water heaters through there. And again, on the water tube side, we offer indoor, outdoor models along with all the copper fin products. So not to go too crazy with that, but the ranges on our offering there is from 199 up to 10 million BTUs. So we have again, full offering there. So to get into the heat pump, where this all stems from is really reducing the carbon footprint out there. So there is like 3 critical segments out there and how they're going to reduce the carbon footprint. Vehicles probably being the number one, industrial process, buildings, specifically with heating and cooling. Okay, so that's going after. And the US goal is to reach a net zero emission economy by no later than 2050. So that's a long ways away. But if you on the next slide, I'll show you, you'll see that a lot of states are really starting to start this process. I think we're a little ahead of the game on some of it, just because as we go air to water heat pump or any electrification there, where do we get the electricity from, and how are they generating that? So I think on that side of things, you know, the United States, the US has to really look at that as well if they're really going to try to reduce the carbon footprint. But US goal for carbon pollution free power sector, so that's the power that's being generated, is in the 2035. So that's coming somewhat quick. So just to give you a kind of a broad overview, and there's probably more to this that I don't even know yet, but if we're looking at New York City, you know, they're really looking at retrofits, and they want to reduce the carbon footprint by 40% by 2030. Okay, so all buildings over 25,000 square feet will be mandated to start that at 2024. All right, so, you know, they're starting to offer some sort of rebates out there in Long Island. But now if we go into California, where it really matters for you guys is, you know, they have $1 billion approved for electrification. Berkeley, San Jose mandates no gas on single family homes, which I have seen out there in Northern California, that they really are starting to just push, you know, heat pumps and electrification. They don't want to burn oil or natural gas at that point. And then just a glance at DC, Washington, DC, they're trying to do the same thing, carbon neutral by 2050, 50% or 2032, relative to like the 2005 standard there. Chicago following suit, the same as the DC, and then New England, where I actually live, they are really trying to get that goal of 100% clean renewable energy by 2035. So there'll be a lot of solar being implemented across, I think, the whole country at that point. So getting into the air source heat pump, you know, what is an air source heat pump? So an air to water, and that's what this is. So we're taking the thermal energy out of the air, okay? And we are even at like low ambient temps with this product. So there's still energy in the air, even if it was 0 degrees out, and we are transferred to a warmer place. So in this case, we are taking the energy out of the air, we are putting it into the refrigerant, which is now turning into putting it into the water. Okay, so water is our medium here. So we're using the water to transfer that cold or hot water and that energy. Okay, so, you know, air source heat pumps, they are gaining popularity across North America. I actually, prior to this position that I'm in with our boiler division, I worked for the Space Pack division, and I sold air to water heat pumps residentially for 13 years, and in California being a very hot market for that type of product. So now we're moving into the commercial world, or even like as I go through this product, you'll see the size range is, it could even be some high-end homes, big homes that this product could fit into. So benefits, right? So environmentally friendly, like we're talking about, green technology. The enhanced vapor injection EVI inverter compressor. So just give you a little bit on this, and I won't get too crazy, but it's a cold climate heat pump. It's like a third small internal plate heat exchanger called like an economizer. And within that refrigerant cycle, they're utilizing a bypass valve that is now taking that refrigerant vapor they're getting from that economizer. So it's a warmer refrigerant, and they're injecting it into the head of that compressor. So now that it's kind of matching in with that colder refrigerant and this warmer refrigerant, and giving us higher pressures and being able to adapt to get that low temp heating out of it. And what this EVI does is it really increases the heating capacity by about 20% than a standard compressor. All right, so EVI inverter. So it's a full modulating compressor, which I'll show you as we go through this presentation. So the capabilities are down to -20 as far as heating goes, and we can deliver up to 140-degree water. And I'll show you some curves on that and what to expect as far as BTUs out at a given outdoor temp. User-friendly touchscreen control, pretty much walks you through everything. No refrigerant handling, because this product, I like to say, it's like buying a refrigerator. It's already pre-charged, ready to go. All you're doing is piping and putting power to it, and obviously a pump and things like that. But it's pretty simple on that side of thing. And then the built-in redundancy, I'll show you that as we go through, but there is 2 independent refrigeration circuits on this product. So let's just say did bring a leak or a compressor did fail, you would still be able to operate half as well. So all for low ambient temperature, that's so if you ever need. I'm starting to see projects like that. I think it's starting to kind of, in a way, almost an unknown what to do here. So they are almost speccing boilers as a whole. Tracy, Austin, I just want to make sure you guys can still hear me.
We lost you for a minute there, Ken, and you were breaking up quite a lot.
Okay, but I think we're better now. I apologize, everybody. I'm kind of in a car doing this just because I'm traveling back from Pennsylvania. But I'm not sure where I hit, but I think we got the point on the low ambient temperatures that this thing's able to perform 140-degree outdoor outlet water. What I was getting into was kind of having, if you have a system already installed out there with boilers, and if you want to reduce that carbon footprint, you know, adding a couple of these heat pumps to that might cover what the state of California is looking for on that side of things. And I'll get into a little more detail of that as we go through this. Okay, so high efficiency. What we have is large surface coils. As I mentioned, we really want to transfer that energy out of the air into the refrigerant, and then the refrigerant to the water. So the bigger the surface area, the more efficient it will be. It's the same as a boiler. The bigger the heat exchanger, the more efficient it will be. So it's all about surface area there. It's as far as the fans on it, those are ECM fans, so they are fully modulating, ultra quiet, and they are the actual fans. So the axles on them, basically that air is coming up through the shaft of those fan motors, and it's cooling it at the same time. So it's again making it more efficient, so they're not running hot. Vertical drain. So basically, and you won't see this in Southern California, but if it was freezing out, you would there's a pan heater in there, and then you have the vertical drain. So if we're into defrost, we're just draining that condensate out. We're not going to freeze it up. Okay. And then up down structure, sealed compressor space to reduce noise. So down in that lower cabinet, those 2 gray doors, that is sealed. And there is what I'll call almost like an egg crate type of foam there for sound attenuating. And again, super quiet operation. This is somewhat redundant on what I already said, but again, on the heating ambient temp. So if we're doing heating with this product, -20 to 109 degree Fahrenheit. Cooling ambient, we can go down to 59 degrees without a parameter change. If we did want to do low ambient cooling all the time, we can go down to 5 degrees if needed. Water temps, as far as heating, say this was being used for like a process heat type thing. We can heat water from 59 to 140 degrees. And then we can also cool water from 44.6 to 95 degrees. So there are some options there. Over on the high efficiency side of it, so we have a COP of 3.4, 3.04. That's us rated at design temp that, HRI makes us do that. And then you have your IPLV, which is it's your impartial load. And that's basically because it's an inverter, they're taking it as it modulates and then coming up with an efficiency value there. So that's a pretty nice thing to look at because again, it's the integrated part load value. is what it is, okay? And then separate modules will allow a unit to work independent of other, providing system redundancy and maintenance, like we talked about, even on defrost. So I'll show you that in the next couple of slides. If you guys don't know what a COP is, I just want to give you a quick definition of it. Is coefficient of performance is what it's really called, COP. And just to make it simple, let's just say you had straight resistant electric heat, or even an electric water heater. You spend $1, you get $1 worth of electricity. Well, when you use an air to water heat pump or any heat pump out there, you're taking the energy out of the air. So now you're spending $1 for the electricity, but you're getting $3 worth of power out of it. Okay, so that's where a heat pump comes into play if we are going in this carbon reduction direction. So these things are way more efficient than going straight electric. So just some capacity stuff. I want to go through this. This is all available on our submittals and everything, but I'll just run down this real quick. So capacity range is really about 100,000 BTUs up to 288,000 BTUs. You have your power input range. So your KWs range from 13 to 28 KW. And a lot of this is based off that it is inverter. So you have your hertz of, 30, 60, 90. And that's how we're kind of rating it that way. Power input range. Hold on, I don't want to tell you that one. Let me just go here. I think the most important thing for you guys to know would be your voltage and your phase. So it is a 460 3-phase 60 hertz powered unit. If we need to go, let's say it had to be 208 3-phase, we'd have to start looking at like a buck boost transformer, which we can spec for you. We don't currently offer them with the product, but we can definitely help spec those if it comes down to it. I think the amperage you want to look at is these are 60 amps per unit. So we want to keep that in mind. Pressure drop on this. So we rate it at 75 GPM, which is your max flow on this product. And you're looking at about 23 feet ahead just through the unit. And I'll show you a cutaway of the heat exchanger so you get an understand there. So I mentioned max flow being 75, but the min flow is 44. So you can vary the flow a bit, but just having a constant speed pump is not a bad idea on these. More flow is not going to hurt it. Less flow could. So just keep that in mind. And then your water connections, they are 4-inch. So they are a flange connection there, 4-inch flange. And then here, I think this is something that's probably most important for you guys to take away. And again, this is part of the submittals too, but looking at your heating capacities and what you're looking to do for an outlet water temperature. All right, so we're showing it at 3 different speeds of the compressor, 90, 60, 30. I'm just going to keep it simple. In your guys' world, let's just say it got down to 40 degrees in Southern California and we're doing heating at 90 hertz. You're just going to follow that up and you should be getting a capacity of close to 300,000 BTUs out of this product in heating. Okay. And it changes as we go to different water temps, not drastically, but they do. So if you wanted to supply 120 degree water at 40 degrees, you're going to be somewhere around 275,000 BTUs coming out of this unit. So if I move on to the next, which is 140, that's the max water temp we can put out of this. And I look at that 40 degree mark again, we are somewhere, maybe 245,000 BTUs, because now it's working harder to get that water temp up, but it can do it.
Hey, Ken, really quick, I got a question here from Joe Pertukas about the availability of a domestic to a domestic capacity, so NSF 61.
So is that being for domestic hot water?
Yes, that's related
All right.
to.
Yeah, so just so everybody knows, this product is a single wall heat exchanger on the shell and tube side. So it cannot have domestic water going directly through it. Now, that being said, you could add a secondary plate heat exchanger on the water side and do domestic that way, or some type of indirect water heater. I've also seen some people using electric water heaters. So they have electric backup and then they're feeding it through that as well. But Currently, this is really more of a heating cooling unit, not really doing domestic water unless you're going to add some extra heat exchangers to be able to do that.
Perfect. Thanks, Ken.
Yeah, no problem, no problem. So just to give you guys an idea of dimensions on this product, this is kind of a cutaway drawing, but you'll see that it's about 86 inches in length, 46 inches wide, and 84 inches high, okay? And just kind of give you a look at that shell and tube heat exchanger. So it's extremely insulated, and you're just seeing this part now. You see your flanges, your flange connections. There is a flow switch here, so if you don't have the flow, the unit will not operate. In though that
Hey, Ken, I think we've lost you again.
that's where the compressors are. So they, can you guys still hear me? Yeah. Can you hear me now, Tracy?
Yeah, it sounds like you're back.
Okay, sorry about that. All right, so I don't know if you guys heard me, but what I was saying is in that tan box, those are where the compressors are. So basically they're double sealed to make any noise. So they're in that box, not to make noise, and then you have the outer jackets that go around it. So that's what makes it very, very quiet. So on the shell and tube heat exchanger, this is what they call a flooded evaporator coil. So this is where your phase changing is actually happening on the refrigerant, whether it's going from the liquid to a gas or a gas to a liquid. But on these tubes that you're looking at, you can kind of see the cutaway. The water flows through the inside of that tube, and your refrigerant phase changing is happening on the outside of that, so inside the shell. It offers an electronic expansion valve, so we call them EEVs, and they make sure that the heat pump adjusts efficiently and accurately. So it really comes into more play when you're doing cooling. So your cooling capacities will improve more than 10% than a standard like heat pump in the running range. And the reason it's doing that, it's trying to match that perfect subcooling as it's cooling. So, which is nice because now it's matching that. So the compressor is ramping down or ramping up, and the EE valve, the expansion valve, is also doing the same, whether it's opening or closing, versus your standard TXV valves, which are wax driven, temperature driven, and slow to react. So these are reacting fairly quick, and also helping to increase the efficiency and the capacity. So modulation, I won't go too crazy with this, but this is just showing the difference between, let's just say, an on-off unit. Okay, it's either on or off, and you're going to have these dips in your curve. You're going to be on, you're going to be off, you're going to come back on, you're going to go off. Well, with the modulating compressor, the inverter, you'll see on this green line, we're kind of ramping low, then we ramp up, we ramp down, but we continue to run. So that really saves a ton of energy as well. Because let's just say it was the on-off one was 60, 90 amps. That's what it's going to pull every time it starts. So that's a big influx of energy at that point. So just like you've all learned about modulating boilers, you want to keep these things running. You definitely don't want them on and off, and unless they need to be off at that point. And precision water temperature control. Also, if you're able to match the load, you should be able to hold your water temp. If I was on off, I could hit that target temp. I'll be off for 5 minutes. I come back on. I got to work hard to get back to that temperature. With the modulating aspect of this, we're really ramping up and down just to keep the steady delivered water temperature. So DC inverter compressor, fans adjust the running speed according to the heating demand and the ambient temperature. That's something that's also a factor in the heating side, that these fans could slow way down, or they could even turn off to make the coil think it's warmer out than it actually is. So that's another feature of how you get these capacities out of these. And then just to hit on that noise, so unit operates as low as 56 dB at 3 feet away. And if you look over on this chart, it kind of gives you an idea, you know, compressor, fan on high speed, you'll be looking at, you know, just right around that 60 D or actually, what is it? It's about 68 dB there. And you're also looking at your compressor. So that's ramping up to a possible of that same dB around that 68%. And then as we go lower, that's where we are running in that 56-ish dB there. So again, if you hear them run live, you'll understand what I'm saying, that they are super quiet. So the smart defrost function on this, and I could see this, you guys could be in defrost a lot if you are in heating. It's all done by pressure. So there's a low pressure sensor. As the pressure goes low, because your coils are icing up, it will go into defrost automatically. As once the refrigerant pressure gets back up to stable, it will take itself out of defrost, which I find to be a really nice feature, because I'm used to, in my old days, they were every 50 minutes, the unit would go into defrost for a certain amount of time, whether it needed to or not. So that was a waste of energy. With this type of design being off pressure, it's only going into defrost when it needs to, which will really make it more efficient at that point. So the independent dual system design, as I mentioned, they're independent circuits. So you could have half the unit in defrost and half in heating, which is a good thing, because when they are in defrost, they're moving cold water, and when they're in heating, they're moving hot water. So at least here, if you have half the unit in defrost, the other half in heating, you're kind of offsetting it, so you don't necessarily need some type of resistant heat or even gas heat to make it when you go into defrost. And this, the energy management system, so as they're staging, each one of these units will do their own internal staging based on whatever water temp you set it to. Oh, can you hear me now?
It sounds like you're back.
There we go. Yeah.
Okay. Yep. Damn crossroads here in New York. Sorry. Okay. So I think you heard me on the energy management, but I'll touch it again. So you could have, you know, as they're staging, you could have one circuit running at 100%. You could have one on off. You could have them both running at 50%. Again, these units are going to do their own internal staging. And now if you're tying multiple units together, they would be staged individually based off the building automation system on the building currently. So control board design, what you guys are looking at over here is your DC inverter drive with all those capacitors on there. And what we've done here is they also added, if you go to that second picture over to the right, there's a little heat exchanger there. So when in cooling, let's say it's hot out, we're using it for cooling, we don't want that board to overheat. It's the same as a VFD drive on a pump, like in a boiler room. We don't want that thing to overheat. So what they did is they put a little heat exchanger in with the control. So when it's in cooling, it's actually cooling the
Hey, Ken, we lost you again.
I think it's really neat. Oh, can you hear me now?
Yeah, you just came back.
Okay, so I'll start on the control board again. So this control board is what I want to tell you guys is every single wire is labeled. All right. And let's just say the board throws a fault, it's inlet water temperature sensor. You'll be able to find that sensor, it'll be labeled, and you'll be able to trace it back if it ever had to be replaced. Okay. So that's one of the
Hey, Ken, I think we lost you there again. Here. Just a moment, everyone. I think we're just waiting for Ken to get back on here. Sorry for the delay. Hey, Ken, are you back? Can you hear us okay?
Can you guys hear? 1 second.
Sounds, I think, coming back in now, Ken.
Can you guys hear me?
Yeah, we can hear you now.
All right. All right.
Yeah, it's coming in and out quite a bit.
Done. I apologize. This okay. Can you hear me now?
A little bit. It's still a little bit shoddy, but you still there?
How about now?
That's better.
Yeah, can you hear me? This is better? Okay.
Yeah, that's better.
Oh, all right. So I'll continue on. Again, I apologize everybody for this. But I just wanted to break out this control board for you. I'm hoping you heard what I was saying about
Hey, Ken, I think we're losing you there again. The sound's coming in and out.
You'll see close
Hey, Ken. Ken, you there? Yeah, I think at this point it might be a good idea to try and reschedule this. I do apologize, everybody. It seems like we're having some technical difficulties we can't get past with the connection with Ken here. Very sorry about that. We'll have to reschedule this to a different time. I will keep everyone posted on what time that will be so we can continue the webinar. But again, thank you very much for attending. I'll keep you posted on when we'll be able to reschedule this webinar. Thank you very much, everybody. Have a good rest of your day.